Good day, everyone. Uh, we are going to design a small farm reservoir project in Lower Paatan, North Cotabato. A small farm reservoir is a valuable water management infrastructure designed to address the needs of small-scale agricultural operations, with an increasing focus on sustainable farming practices and the need for efficient water usage. Small farm reservoirs have emerged as practical solution to mitigate water scarcity and enhance agricultural productivity. Typically, a small farm reservoir is a man-made water storage facility strategically constructed on farm rural properties. It serves as a reliable source of water for irrigation, livestock, and other farming activities, particularly during dry period or when water supply is limited. These reservoirs are usually created by damming small streams, diverting water from nearby source, or excavating the land to create a storage basin. The location of Reservoir is in Lower Paatan, Kabacan, North Cotabato. The factors that we need to consider is average annual rainfall, which has 2,099.59 mm per year, slope that has 0% because it is a dug-out pond, soil texture which is a clayly loam. This is the design of small farm reservoir. The soil texture is clay loam. Based on geoportal, the soil texture is clay loam. The dugout pond capacity is computed by surface area times the depth. The surface area, which has a length of 50 meters and width of 30 meters, with the area of 1,500 meters squared, and the depth is 2.3 meter. The dugout pond capacity has a 3,450 meter cube without the freeboard. The velocity of the wind is 0.37 km per hour, or 370 meter per hour. To get the freeboard, we need to get the freeboard we use in PA is 2 to 6 as a reference. So the formula for freeboard is 1.5 times the times 0.032 times square root of fx, which the f is 50 meter or 0.05, plus 0.763 minus 0.271 square root of f. So our freeboard is 1.26 meter. The design height is ID plus freeboard is equals to 2.3 plus 1.26 equals 3.56 meter. The final height is a finished height is equals to 3.58 times 2.2 equals to 0.716, and finish height plus the 20% of the design height is equals to 4.296 meter. The capacity with freeboard is computed by multiplying the area times the finish height with the finish height. So it is 1,500 meter times 4.2916 equals 6,437.4 meter cube. This is the design for the small farm reservoir, which has 1,500 square meters, based on PAES, which has that we need 1,500 meters squared of area. And unimodal rainfall pattern, the T is equals to 2099.59 mm per year. Based on table 2 in PAES 226, the grassland is equals to 0.8, and in every 100 meters squared is equal to 0.6 hectare. Then I choose a 1 hectare. Pond area is equals to 1,500 meters squared over 1,000 meters squared is equals to 1.5 times 1 hectare is equals to 1.5 hectare catchment area. The average rainfall per month is equal to 174.97 mm. Since the average rainfall is 2,099.59 mm per year, divided by 12 is equals to 174.97 mm. Divided by 1,000, it becomes 0.1749 meter. Estimated volume of water to fill the pond. Capacity with a freeboard of a ERF So to get the ERF, we need to multiply the average rainfall times the pond area. So it becomes 2,624.55. So to get the volume of water to fill the pond, capacity with freeboard over ERF is equals to 2.4527 months to fill the pond. We don't have outlet channels because it is a dugout pond. The inlet channel's depth is 0.75 times 2 equals to 1.5 meters. Water obstruction technique is pumped because the water level in the reservoir is lower than the service area. The catchment area is 15,000 meters squared. The average rainfall per day is 5.752 mm per day times 1 meter over 1,000 mm to get 0.0058 meter per day. The volume of actual rainfall per day is equal to catchment area over ARF, which is 86.28 meter cube per day. This is the catchment area in Google Earth Pro. To get the surface area, we need to get the crop water requirements. So ETO is equals to P times 0.46 T mean plus 8, which from Pag-asa website, the T mean is 26.65 degrees Celsius. So the ETO is equals to 5.67 mm per day times 1 meter over 1,000 mm times 1,500 meters squared of area of reservoir is equals to 8.512 meter cube per day times 365 days for 1 year. We have the ETO of 3,106.76 meter cube per year. The crop coefficient of palay is 2.85. So to get the evapotranspiration, we need to ETO times the crop coefficient. So 5.674 mm per day times 2.85, which has a result of 16.17 mm per day. The CW, the crop water requirements, is we need to get the crop water requirements. So evapotranspiration plus SP is equal to 16.171 mm per day times 1.75, which has a result of 28.30 mm per day. For seepage loss, 1,500 meters squared times 0.001 meter per day equals to 1.5 meter cube per day times the 365 days, so 547.5 meter cube per year for seepage loss. For land soaking requirements, LSR is equals to N minus RMC times AS times DRZ over 100. This is from PAES. 49 minus 13 times 135 times 200 mm over 100 because of the clay loam properties. So the LSR is 94.35 mm, while the LPWR is equal to LSR plus SW plus ETO, which is 110.024 mm. The efficiency rainfall, we need to, the formula is 0.8 P minus 25, since our precipitation is equals to 174.96 mm per month. So 0.8 times 174.96 minus 25 is equals to 114.968 mm, and our EA is equal to 60% or 0.6 because of clay loam. For farm water requirements, the formula to be used is the CWR equals to ER plus LPWR equal over EA, 28.30 mm per day minus 114.96 mm plus 110.024 mm over 0.6, and our farm water requirements is 38.93 mm. So to compute the surface area or service area rather, the capacity, we need to divide the capacity by FWR, and our capacity is 345 meter cube over 0.0389 meters. So our service area is 88,688.94 meters squared divided by 10,000 to become an hectare, which is 8.87 hectare. So this is the service area, which is the blue, by the using of Google Earth Map Pro. In conclusion, SFR play a crucial role in enhancing agricultural productivity and ensuring sustainable water management by providing a reliable and controlled water supply. They empowered farmers to optimize their farming practices, mitigate water scarcity, and contribute to the conservation of the water resources. As the demand for food production grows and climate change impact water availability, SFR will continue to be an indispensable asset for small-scale farmers, fostering resilience and sustainability in the agricultural system. That's all. Thank you.